All right, the next theorem is Rolle's theorem. And after we talk about this, we're going to go ahead and do examples 8 and 9, which have to do with Rolle's theorem. So Rolle's theorem basically says that if you have a continuous function defined on a closed interval, and you know it's differentiable on the open interval, if you know the value of the function is the endpoint, the value of the function at the endpoints are equal, then you know there's a place between a and b, strictly greater than a, strictly less than b, where the derivative at that location c is 0. Essentially, what we're saying here is, here's a picture to go along with Rolle's theorem. Here's our a, here's our b. And if our function's continuous and we know that at a and b it's the same, well, how many ways can you connect a and b? Well, you could do the straight line, and then that means, well, everywhere here the derivative is 0 since it's a horizontal line. Or if you go up, well, there's no way we can connect to b continuously unless we turn around. That means we go up, positive derivative, then we have negative derivative. That means there has to be a 0 derivative at the top. Essentially, Rolle's theorem says that what goes up must come down, or what goes down must come back up. So the only way that we can continuously connect these 2 points is if at least one location, sometimes there's more than one location, we have a horizontal tangent line. So let's verify Rolle's theorem for this function. So in order to verify Rolle's theorem, we want to check that the value of the function at the endpoints is the same. So let's check to see what we get when we plug in -2 and 2. When we plug in -2, we get 12. When we plug in 2, we also get 12. So these two are equal. So that's the first hypothesis of Rolle's theorem. We're also going to go ahead and say that since this function f is a polynomial, we know it's continuous. So f is continuous. Not only is it continuous, a polynomial is continuous and differentiable everywhere, so we know that f is differentiable on the open interval. That's true. If it's differentiable on all real numbers, well, then it has to be differentiable on this smaller subset of the real numbers. So these hypotheses are all satisfied. So now we want to see, is there a location where the derivative of this function is equal to 0? Because Rolle's theorem says it exists. So let's go ahead and take the derivative, which would be 4x cubed minus 2x. Let's go ahead and set this derivative equal to 0 and solve. We can divide each side by 2, and then we can factor out an x to get 2x squared minus 1 times x. Well, this provides for us 3 solutions. X is 0, x is plus or minus 1 over the square root of 2. So there are actually 3 locations between -2 and 2 where the derivative is 0. Rolle's theorem says that there exists a c. That doesn't mean there exists exactly one value of c. It just says there could be, at least there's one. Could be 5, could be 30, but there's always definitely at least one. So that works out. The hypotheses were satisfied and the conclusion followed. Example 9. Suppose that f of x equals 1 minus x to the 2/3 power. Show that the value of the function at the endpoints -1 and 1, they are equal to one another, but we can't find a value c between -1 and 1 where the derivative is 0. Why does this not contradict Rolle's theorem? So, first thing we'll do is we will show that f of -1 is exactly the same as f of 1. So f of -1 is, well, this would be 1 minus 1, which is 0, and 1 minus 1, which is 0. So again, these two are equal. But there's no c in this open interval. So let's go ahead and try to find that c. So we take our derivative. We're going to have minus 2/3 x to the negative 1/3. And if we choose to write this as a fraction, we have negative 2 over 3 times the cube root of x. Now if we set this equal to 0, the only way that a fraction is equal to 0 is if the numerator of that fraction can be made equal to 0. That's the only way it's possible. Well, there is no variable up here in the numerator. So is 2 ever equal to 0? No, 2 is 2. So, in fact, this is never true. It's impossible. So because of this, well, we've shown everything that the problem told us was going to happen. But the question is, why does this not contradict the theorem? Because we've shown that they're equal, but we can't find a c. Well, we didn't really show that all the hypotheses were true. What are the other two hypotheses that we didn't talk about? We didn't talk about continuity or differentiability. So f is actually continuous on negative 1, 1, but it isn't differentiable at x equals 0, which x equals 0 does live inside here, so it's not differentiable at x equals 0, so this implies it is not differentiable on the open interval negative 1 to 1 because 0 lives inside there. What's the issue? Well, here's our derivative. If we plug in x equals 0, we get division by 0, which breaks the function. The first derivative has a discontinuity, an infinite discontinuity at x equals 0. So this function here cannot be differentiable at that location. So it's the fact that it's not differentiable that allows for us to not be able to find this, or what prohibits us from finding such a derivative being equal to 0. So it does not contradict Rolle's theorem, because not all the hypotheses of Rolle's theorem were satisfied.